To start our journey into SQL, we'll first talk about the select operation. The basic structure of a select statement says select column 1, column 2 through column n, some list of column specifications from the name of a particular table. We can also specify all columns in the table by using the wildcard star operator. The purpose of the select operation is to take up data from the table and to give us the data that's in those specified columns from the table. We can also specify that we only want data from particular rows in the table using the where clause. The keyword where allows us to specify conditions such that only the data in particular rows from the table will be returned. So the select operator, together with a where clause, corresponds in relational algebra terms to the combination of a projection operation to the result of a select operation. We do a select on the condition from that particular table, and then use projection to project the result of that selection, those particular rows from the table, onto only specified columns. So, for example, we might have a database of books, and we can select the title and author from those books which are fiction by saying select title author from books where genre equals fiction. In this case, this statement will take all of the rows of the books table where the genre column has the value fiction, and then we'll return a table that includes only the title and author from each of those particular books in the specified columns. Now, a where clause can have a variety of different conditions depending on what kinds of comparisons we would like to make with the values stored in particular columns. So we have the standard mathematical operators, equality, non-equality, greater than, less than, greater than, equal to, less than, equal to, and so forth, which compares the column values to specified values. So we might use this statement, select star from orders, where quantity is greater than 4, to find those rows in the orders table where the quantity is larger than 4, 5, 6, 7, 8, all of those rows would match and then be selected. When we say select star again, that means select all of the columns of data from the specified rows. For string matching, we can use the equality operator or the not equality operator. We also have the like operator, which matches a string to a pattern that can include wildcards. So it's used in the same way that other comparison operators are used. We have the where column like a pattern, where the pattern is a string which can include the percentage sign as a wildcard, which matches any sequence of characters in a string. So we might say select name from employees, where name like the string a percentage, which will select all the employees whose name starts with the letter A. We can also combine conditions by using logical operators. We can use and, or, and not. So we might say select something from employees where the age is greater than 30 and the salary is greater than 50,000. Or we might select where the department equals sales or the department equals marketing. It could be this value or that value. We might combine logical operators in more complex forms where the department is not sales, not department equals sales, and either the age is less than 30 or the salary is greater than 50,000. And so on and so on. We can create arbitrarily complicated conditions within the where clause to select particular rows from the table. With the in keyword, we can specify a set of possible values such that we're asking, does the value in a particular column match any one of those values? So we can say, find all of the rows in the orders table where the product is either apples or bananas by specifying that it has to be in that particular set. It's a different way of specifying. We could specify product equals apples or product equals bananas, but it's much more concise and makes much more sense to say the product is in a particular set. We can do something similar with numeric values with the between keyword. We can say select something from a table where the column name, where the value in a particular column is between one value and another value inclusively. So we can, for example, select all the data from the orders table where the quantity is anywhere between 3 and 7. So 3, 4, 5, 6, 7, all of those values for quantity would count, and those rows would be returned. Again, this syntax is more concise and expresses more precisely what we'd like to do rather than saying it's greater than this and also less than that. When we're looking for data in our database, we don't always want to find the data as it's expressed in the database, but sometimes we want to summarize the data, to roll it up, as is sometimes said. And one way to do this, probably the most common way to do this, is through what's called aggregation. In aggregation, we take the data from a column in a number of different rows and aggregate those values together to form a summary value for that set of values. We might aggregate finding the average, finding the sum, finding the number of values, and so forth. And we do this by saying select aggregation function applied to some column from the table. So to give an example, if we want to say how many customers do we have, we say select count star from customers, and that will give us, as a result, a table that includes one column labeled count star, which has exactly one row, one value, which is the number of rows in customers, the number of times we see any data in the customers table. And we can count, we can create averages, min, max, sum. Those are the most common aggregation functions used. Here are some more examples. Select sum of salary from the employees. That will give us a value which is the sum of all of the employees' salaries. Again, looking at all of the values in the salary column, adding them up, and returning that in the results table. We could similarly select the average age from students. This will calculate the average age of all of the students. Look at all of the ages, calculate their average, give you that number as the single result. We can also do multiple calculations. We can get back a table with more than one column. Select the min price and the max price from products. Both min price and max price are looking at the same column in the products table, price, and one will compute the minimum over all the values, the other will compute the maximum over all the values. We'll get a result table which has exactly one row with two columns, the minimum and the maximum of the prices of all the products. This is very useful, but what's more useful is if we can relate aggregation to other attributes of the data. We don't necessarily want the average over all the salaries of all the employees in the company, but maybe we want to compare employees in different departments. Instead of saying select some salary from the entire employees table, what if we want to know the sum of the salaries of the employees in each particular department? We can do this using the group by keyword. Select department and the sum of salary from employees, group by department. What this is going to do is it's going to take all of the data in the employees table and look at each department separately. It says all of the employees where the department equals one thing, sum their salary. Employees where the department equals another value, sum their salary, and so forth through all of the different values in the department column. Then we will get a summary table which gives us, for each department, the sum of the salaries in that particular department. The general form of aggregation using group by is select a column, the aggregation function applied to that column from a table, group by that column. Now notice, you have to specify the column that you're grouping by in your result columns, because if you don't, you won't know which group each value of the aggregation corresponds to. So as we saw before, we had to specify department. So we can say, for this department, we have this sum. For this other department, we have another sum. So you have to specify the column in all of these places so you know what you're grouping by when you get the result. Now, we don't have to group only on all of the data. We can also use a where clause to specify we want to do grouped aggregation only on a subset of the data that matches a particular condition. So we might say, select department average salary from the employees table, where salary is greater than $50,000. So only look at the employees whose salary is greater than $50,000, group by department. So now we'll get, for each department, the average salary of the employees making more than $50,000 in that particular department. One thing that you might have wondered is, if I select only a specific column from a table, what happens if there are duplicate values in that column? In relational algebra, all relations are sets. So when you get back your result, it will have no duplicates. In SQL, however, a table doesn't have to be a set. You can have duplicate rows. This is one of the ways in which the practicalities of implementing SQL means that deviates slightly from the theoretical assumptions from our theoretical model of relational algebra. So if I say simply select department from employees, I may get a table like the one here at the right, where the finance department is listed twice because there are two different employees in the finance department. It's just going to select that column and give it back to me with duplicates. If I want to ensure that all duplicates are eliminated, that I'm actually getting a set rather than a table of values that might have duplicates in it, I use the keyword distinct to specify I want distinct values in each of the rows of my result. So if I say select distinct, column 1, column 2, and so forth from table name, that will give me distinct values for every row of the result. In our example, select distinct department from employees will not duplicate the finance department. It will only be listed once because I'll get a distinct value in each one of the rows. We can also, in a select statement, rename the columns that are going to be returned. That is to say, we'll select data, but we'll get back a table where the columns have different names than they did in the original table. So if in our employees table, we have a field, a column with the name of name, in our result, we might specify we want to select name as employee underscore name, which means that in the result, the resulting column is going to have a different name than it had in the original table. And we can do this for any of the columns of our result. So we might select name as employee name and salary as employee salary if we wanted to, and they would be renamed. One of the reasons why we may want to do this is that in select, just as in the projection operation in relational algebra, we don't only have to select values from columns as they are, we can perform calculations and get a result column with a calculated value. So for example, we might want to project what would happen if we gave all of our employees a 10% raise. That would be awfully nice. And we might say select name, salary, to get the original salary, and then salary times 1.1 to get a increased salary, a computed salary after the raise. We can then rename that column to increased salary using the as keyword as before. So select name, salary, salary times 1.1 as increased salary from employees will give us a table with 3 columns, name, salary, and increased salary, which will have the relevant values for every one of the employees in the company. One other way in which SQL differs slightly from relational algebra is that a table has a particular order that the values come in, and you might want to get your result in a particular order. So you can specify what order you'd like them to be in by sorting on a particular column. Order by will sort the result set either in ascending or descending order. You can say select some set of columns from a table, order by one particular column, either ASC to indicate ascending order, or DESC to indicate descending order. If you don't specify, the default is ascending order. So we might want to look at all of our employees in descending order of salary. So select name salary from employees, order by salary, DESC for descending order. You'll get first the employee with the highest salary, the next highest, and so forth. We've covered a lot of material here just in this one select statement. Fundamentally, a select statement retrieves data from a database. It finds data that matches a particular condition and gives it back to you, maybe selecting particular columns and not giving you all of the columns in the table. However, we can also do a lot of different kinds of data manipulations and moving data around within just the select statement. We can aggregate data, we can compute functions of the data, we can move it around, we can rename it. We can do a lot with a simple select statement. But now think about, what if we have select statements and we take the result of a select statement and put it into another select statement, or other kinds of operations that we're going to learn about soon? Putting together these fundamental primitive operations, which in and of themselves are also fairly sophisticated, you can create highly sophisticated, highly complicated queries that do very sophisticated computations over data. By learning and understanding the foundational principles and the fundamental operations of SQL and relational algebra, you will gain access to the full power of relational databases.